a graduate student here at University of Illinois. I'm going to talk about forward modeling AGN variability. So another exciting topic that we haven't heard so much. So please take it away.
Great, thank you very much. All right, thank you very much to the organizers. I've had a great time hearing all the talks so far. So despite the name of this conference, AGNs don't go boom usually, they more flicker. So this is an example, light curve of an Seyfert galaxy in AGN. We think the AGN variability comes from the fluctuations of the accretion disk, if you're looking in the optical. And I'm excited to tell you about some of my work trying to model AGN variability selection for LSST. And I also highlighted my collaborators, and the local people are in the Illini orange colors. So a little bit of motivation for why I'm interested in this. So this is a slide going over black hole demographics. So the basic idea is there are observations of high redshift quasars with very massive black holes, and how did they get that big so quickly? And the other piece of evidence is we know that basically every local galaxy is thought to have a supermassive black hole in its center. So the thinking is, in order to get all of these supermassive black holes that we can observe today and in high redshift quasars, there needs to have been some seed black hole that formed at higher redshifts. But the theory is still very uncertain here. And this cartoon shows two popular theories for how you might get a black hole seed at higher redshifts. So this figure here shows redshift versus black hole mass, and it's showing two seeding mechanisms that theorists have come up with. And one is remnants of population 3 stars, and another here, popular one, is direct collapse black holes, which basically a protocluster at high redshifts, gas cloud can collapse into a black hole under really specific conditions. And so those direct collapse black holes are usually referred to as heavy black hole seeds, and the stellar population 3 stellar remnants are usually referred to as lighter black hole seeds, because the mass distribution of those two mechanisms is expected to differ. And over time, those will grow via accretion and mergers to form those supermassive black holes that we can observe today. But some of those seeds, for whatever reason, may not grow as quickly, and we might have a population of leftover intermediate mass black holes in dwarf galaxies. And so for the purposes of this talk, an intermediate mass black hole is somewhere around greater than 100 solar masses, but less than like 10 to the 6 solar masses in terms of the black hole mass. And so the observational tracer of this is the fraction of dwarf galaxies hosting an AGN in them. And so the idea is the mass of the black hole is connected to the mass of the galaxy. And so if you have a dwarf galaxy with an IMBH in it, and you can basically count those, that mass function should trace the different seeding mechanisms. So that's the picture. I'm going to go over this really quickly, but this is just to say that there are strong candidates for IMBHs that have been published. One is HLX1, which is a hyperluminous X-ray source. So it's like these ultraluminous X-ray sources, but in this case, its X-ray luminosity is 10 to the 39 ergs per second, so it's hyperluminous. There's another interesting source which has this telephone number here. And so that's here, and actually it's here in this box, and that's a zoom in. And that's thought to be an X-ray TDE, which is interesting. And then there's, of course, the recent gravitational wave merger, which is kind of a borderline IMBH if you use a definition greater than 100 solar masses. And what's interesting about these is that they're all outside of the nucleus of the host galaxy. And so that's something that you might keep in mind for this talk. Another example is the famous Seyfert galaxy NGC 4395. So this is a dwarf galaxy with an AGN. It's been known for like 10 or 15 years. And Its optical variability is very rapid, so this is a test-like curve, which I analyzed a couple years ago, and the variability timescale is around 2 or 3 days. So this is a month-long light curve. This is work by Vivian Baldassare, who selected AGNs in dwarf galaxies. So the idea is if you have a variable thing in a dwarf galaxy, it's hard to fit a supermassive black hole in like a 10 to the 9 solar mass, stellar mass galaxy. So this is restricted to SDSS galaxies with spectroscopic redshifts and stellar masses from the NASA Sloan Atlas catalog. So not a super deep catalog, but interesting work. And this is a plot of the fraction of variable AGN versus stellar mass of the host galaxy. And what's interesting is that in even these pretty low mass galaxies, there is a non-zero fraction of AGNs, and they all have this pretty convincing stochastic variability on like years time scales or less. But it's hard to learn too much about the AGN population with just the variable fraction because there's a lot of selection effects. You know, dwarf galaxies tend to be fainter. So I've been working on forward modeling this. In order to do this, because the host galaxy is connected with the mass of the black hole, you have to do this in a way that's closely connected to the galaxy stellar mass function. So we started with the galaxy stellar mass function, the best constrained one I could find in the literature, which is from the Gamma survey. And so the red circles here are from SDSS. And so this is stellar mass on the bottom. And the red marks here are from Gamma. And so this is just the double Stetcher function fit to that data. There's some incompleteness here due to surface brightness. After that, we need to assume something that tells us, okay, of all these galaxies with this stellar mass distribution, how many of them have a black hole? And so this is called the occupation fraction. And so we put in 2 sort of toy models for the occupation fraction. One is a light seed model where basically every galaxy has a black hole in it, even the really small ultra dwarf galaxies. And then a more pessimistic model here where the fraction of galaxies with black holes in them decreases sharply around like 10 to the 8 or 10 to the 9 solar masses. And so this one is motivated by some work using numerical simulations. But the theory is still pretty uncertain, so this is just to sort of bracket the possibilities. And this is the correlation between the black hole mass and the host galaxy stellar mass, and that gives you the black hole mass function, which is in blue for the light seeds and magenta for the heavier, more pessimistic seeding scenario. And then just to do something even more crazy, I defined a new black hole mass function here in green, which is anchored to the black hole mass function derived from Cecilia, which is derived from gravitational wave constraints. So that's a stellar relic black hole mass function. And it didn't really consider I and BHs that could form continuously through some of those other formation channels, which there's a lot in the literature. So because I like power laws and I'm an astronomer, I anchored it to the stellar mass black hole mass function here and allowed it to smoothly match up with the black hole mass function for supermassive black holes there. And I'll double check that this is consistent with the observations in a minute. And so after that, you need to figure out, okay, how many of these black holes are actually accreting? And so then we use the Eddington ratio distribution, which is constrained from observations of radio galaxies. And so then finally you get your bolometric luminosity function for your AGNs using some SED, which I don't have time to go into. I'll spare you the technical details. And so again, here's the occupation fraction of 1, optimistic scenario, pessimistic heavy seed scenario with a more pessimistic occupation fraction. And then my crazy idea that's anchored to LIGO Virgo merger rates. And then what's here, these are the quasar luminosity functions from the literature. So that's consistent there above, 10 to the 42 ergs per second. But below there, there's no good constraints on AGN populations. So just to figure out, okay, is this crazy or not, I compared to the luminosity functions, I think I blew this up on the next slide, of ultraluminous X-ray sources. And so these are either hyper-Eddington accreting stellar mass systems, and some might be IMBHs. But the idea here is that if we're predicting a luminosity function that's way in excess of the luminosity function of these ultraluminous X-ray sources, that's probably too optimistic, and we would have detected more IMBHs by now. So this is just kind of to give you an upper limit on what's possible. And then here I did the same thing, but for X-ray binaries and globular clusters. And we find that our IMBH predictions are all consistent with roughly or below those luminosity functions, which is good. Let's see. Okay, good. So what does the AGN variability look like after we've got the luminosity functions of our AGN population? Well, generally, AGN variability in the optical is stochastic, like I showed on the first slide, but the time scale and the amplitude depends on the properties of the black hole. So this is just a cartoon, simulated light curves here on the right. This is white noise, and this is a damped random walk, which is a pretty damn good but not perfect model of AGN variability. And this is the power spectra for the damped random walk in purple. There's the reason it's called a damped random walk is because at higher frequencies you get red noise like PSD, which then flattens out on longer time scales. So that's the damping part. And there's a transition frequency or transition time, which is usually given as tau there, which corresponds to the break in this power spectrum for the damped random walk thing. And so basically the amplitude of the variability depends on the accretion rate, we think, or the luminosity of the AGN. And the time scale, we think, depends on the mass of the black hole. So if I can get to the next slide. So this is some other work which was led by me, which was published in Science last year, and where we looked at a high-quality sample of quasars and AGNs with a really broad range of black hole masses from 10 to the 4 to 10 to the 9 or so solar masses, and we measured their damping or break times from the power spectrum. And I won't go into the details of how we did it, but we find that the prediction here, or the fit here in orange is pretty close to the prediction from the standard model of accretion disk, the Shakura-Suneov accretion disk prediction. And within about 2 sigma, we think that can be explained by some selection effects in our model. But the upshot is that if you, this might be a little controversial, but if you plot accreting nova-like white dwarfs from Scaringhi 2015, that's consistent with this power law of 1/2. So these are optical light curves of stellar mass accretion disks. And if you interpolate between the two, then this gives you a prediction for what the variability timescale of an intermediate mass black hole might be in the optical. And it's tens of hours to a few days, depending on what mass you're looking for. So could we use this as a tool for IMBH discovery and mass estimation in LSST Rubin? I think I will sort of skip the details of how we simulated the light curves, but these are ZTF dwarf AGNs from Vivian Baldassare's paper and some other works. So these are known AGNs in dwarf galaxies there. We estimated their black hole masses, and I think these are from virial broadline masses, if we had them, and measured their variability amplitude, basically in magnitudes, compared to SDSS quasars. And this blue line here with uncertainty is basically our model of what the variability amplitude would look like of an accreting IMBH in a galaxy after accounting for the dilution from the host, galaxy. So lower mass black holes have a higher fraction of light from the host galaxy, so their variability amplitude would decrease. So we really need a high precision photometric survey for IMBHs because we're talking, a tenth of a magnitude or less here. And so here's a predicted light curve from our model for a 10 to the 6 solar mass black hole and a 100 solar mass black hole. And so you can see change in, this is G-band magnitudes. Okay, skip that. So finally, we are able to compare our results to the literature. So the this is again the variable fraction versus stellar mass, and the same thing, variable fraction versus magnitude of the host galaxy. And the red data point here is what I showed earlier from Vivian Baldessare's paper. So that's the variable fraction measured with the PTF observations and from the literature. And the magenta and blue curves here are our two predictions for the different occupation fractions that we input to our model. And so for PTF, they're not really differentiable because there's a limited depth of the survey and number of galaxies at low redshift. So this is all low redshift. But when we ran this, but it is roughly consistent with the observations, which is a nice check. And when we ran this with an LSST-like simulation, using like the baseline 2.0 cadences, I didn't use the full light curves, just putting in the sort of median cadence and survey length and all that with gaps. It's not, the variable fraction turns out is not too sensitive to the exact cadence as long as it's, I'll talk about that on the next slide if I have time. There's some sensitivity there, but in any case, the predictions for the heavy seed here and light seed scenario there can be differentiated in like 2 or 3 sigma, which is promising. So the ultimate idea is to constrain the occupation fraction at redshift 0 with Rubin Observatory and use this model to help us calibrate those observations. But the big caveat here is how well the local occupation fraction actually traces the initial seeding mechanisms at high redshift is definitely an open question for theorists. But hopefully we can put some constraints on this galaxy black hole mass function with LSST Rubin. So this is the recovered black hole mass function for our 3 different black hole mass functions that we inputted to the model. And depending on how optimistic or pessimistic you are, and the uncertainties are pretty huge, but you could find anywhere from 1,000 to 0 IMVHs, depending on, again, the black hole mass function there and for dwarf galaxies. But they can be differentiated with Rubin Observatory, which is very, very promising. Okay, I think I'm going to skip this in the interest of time, but since these AGNs have, IMBHs have really rapid variability, you need a good enough a high cadence to actually measure their masses with the light curves using our relation. And so you can read more about it. If you search, give me a few hours, Eric Bellum and I have a white paper there talking about using LSST for higher cadence transients and AGNs. So there are some challenges that I'll just quickly go over. So the short variability timescales of IMBHs, it's hours to days. So we really want high cadence to identify them. The IMBH need not be in the nucleus of the galaxy. And the small variability amplitude is unlikely to show up in alerts probably. So it's going to be hard to do too much before the data release 1. Not to mention the possibility that these could be transient or changing look behaviors too, complicates things even further. So anyways, I know that's a lot, and there aren't many AGN people here, so feel free to reach out during the conference for other questions. Sorry for going over. Thanks.
Thank you very much, Colin. Super exciting topic we should not forget about, despite there's another conference going on in parallel about the AGN. Yes. So that is just, keep in mind, this is a lot of interested folks and interesting science. Questions, comments from the audience?
Hey, Colin. Really nice talk. I was wondering, what are the current or best time domain surveys that we can use right now to search for these intermediate mass black holes?
Yeah, so TESS is probably not deep enough to find those because their luminosities should be very small. And ZTF, if you get lucky, it's possible. So Kostya and I are trying to mine the high cadence ZTF data release to try to find something, but there aren't good predictions on the luminosity functions of IMVHs, as you've seen. So it's hard to say with certainty. Yeah. But higher cadence is, I think, pretty certain. Yeah.
Any other question, comments? Federica.
Can I just, this is Federica again, can I just ask a clarification about, when you say high cadence, though, you really mean about day cadence, not intranight, right?
Days, depending on the exact mass that you're looking for and how closely they actually follow this time scale mass relation. But yeah, ideally days or even like hourly would be awesome. But you don't need like hourly cadence for a year. You need like a few days, have some
coverage at a few hours time scale.
Exactly. You just want to basically, you just want to sample the power spectrum,
And can you use a 2 meter, a 4 meter, or you need a 6.5 meter?
That's the question I don't know right now, but I think it's going to be hard to do at the 2 meter, I think, given the predicted luminosities. But, yeah.
Great. Any other last question for Colin? Let me just check. Yeah. If not, let's thank Colin again.
Thanks. Yep. Thanks.
And I hand it over to the next session chair.